right, so I'm going to get started. So, as I talked about last year, we often use words like work, energy, power. We would interchange those three words, but these three things are completely different. Well, not completely, but they're just different in enough way that I can't just say, instead of power, talk about work. These are different from each other. So they are very similar. Power relates to these because it is the rate of doing work. So whenever we talk about the rate of something just means divide by time. So if we talk about the rate of change in distance, that means we're talking about velocity, because it's just change in distance over time, or displacement over time. So for power, we've just got power is work over time. That's the rate of doing work. So it's just work over time. And based on our definition for work, we can also write this as change in energy over time. Since work is change in energy, it is going to be up to you to figure out what type of energy changes. You could also look at work equal force times distance, and that's going to be over time, but I'll get to that a little bit later. These are the two main ones that you'll see. Notice the units for power. I can either use joules per second, or watts. So you've seen watts before with light bulbs, stuff like that. How much watts are there in some sort of an item? Whether you're looking at a machine or a motor or something like that. Don't get confused with W for watts, W for work. They're both the same thing. One's a unit, one is a variable. In a while. So continuing on with this, here's an example. Like I said, this set of notes was not made by me, and they're apparently not a huge fan of biology students. So we've got a physics student who's setting up a body slam on a biology student. He's lifting up the student over his head to a height of 2.2 meters in a given time. We want to know how much power did the physics student generate when they lifted this student above their head. So using the above equations, power is change in energy over time. And what type of energy is changing in this case? Kinetic or potential? Potential, why? If something's going up, it's going to have a change in potential. Unless you have a change in velocity as well, then you got a combo of both. But right now we're just dealing with potential, so it's change in potential energy. So this is just, you could write this out as potential final minus potential initial if you want. Or, as I like to write it, just do it like this. Just easier, but totally up to you. And then this also helps you to remind you that you need a change in energy. So a change in height, not just a height. So this helps you with the trick question of something being held still. So we've got the mass, we've got G, we've got the change in height, we've got time. Pretty straightforward. Plug in the numbers, you get 2,400. Yes, W is capital. Any questions on this? Yep. No, you'd have to do, with kinetic energy, you can't just do half m change in velocity squared, because of the squared, you need to square it first before you subtract. It has to do with an order of operations, which we'll get into here. So we've got Mr. Trask, that's who I got the notes from. He is traveling at an initial velocity, then you have a final velocity, you've got time, and you're given mass. We want to know power. And we're going to ignore friction in this case. So again, we're dealing with change in energy. This time, your velocity is changing. So it's change in kinetic energy. So what you could do for this one, if you wanted to write out something like this, you would do a half m and then in brackets vf squared minus vi squared. That's how you would write the shortcut if you want to do it. If that's confusing, just go like this. Final kinetic minus initial kinetic. You've got all the numbers. You've got the mass, you got final velocity, you got initial velocity, you got time. So just plug in the numbers. I'm not going to show you where those come from. And you get 12,000 watts. So based on what you're given in the question, you need to determine, are we dealing with potential or are we dealing with kinetic? And this might get confusing because you might also think, oh, final velocity, initial velocity, time, I can use kinematics. So here's where it starts getting tricky to know when do I use power or when am I using kinematics. And that just depends on, well, right now it depends on the unit. On the final exam, either way is fine. As long as you can solve it, I don't really care. So with this, or any questions on this before I move on?
How would you use kinematics?
Solve for acceleration, gives you a distance. Power is force times distance over time. And also with acceleration, you have the mass, so you know F net. And since you're ignoring friction, there's no friction. Yeah, I mean, it's the same thing, because your force is mg, and then your distance is the change in height. So technically, yes. There's another equation we can use for power. This one I will show you, because it's really quick. So we said powers work over time. We know work can also equal a force times a distance. So I can also say that this is force times distance over time. And if I'm dealing with constant velocity, d over t is a speed. So this could also be another equation you could use, Fv. But based on the fact that this is only at a constant velocity, this equation only works for constant velocity. So this is a good thing to know, and you'll see why in the next one. But this is only in a specific case. So you do not need to know this one as well, but it definitely does help. What do we get? So let's give this next one a try. So we've got a student pushing their giant review packages up and a ramp like this. And we want to know how much power does the student exert. So the problem with this one is typically you would look at, okay, change in energy. Well, the change in energy is potential. I'm increasing my potential by this much, but I don't know the height. I know the angle. You could figure it out. It would just take a long time. You'd have to figure out acceleration, but it's 0. So constant velocity. You don't know any distances. And so that's a problem. But with our power equation, because it says constant velocity, we can do force times velocity. Since it's constant velocity, my forces balance out. So therefore my force is just, force of friction. I also have to do, this is more complicated than I thought. This one's not completed on my notes, so you want to write this one down. So with this one, we've got a bunch of forces. We got Fg, we've got force of friction. We're going to break this up to two components. We're going to have our parallel, perpendicular. You have some force applied up here, and the normal force. So in this question, it says how much power does the student exert? So we need the force that the student is doing. So we first need to figure out force applied. Any guesses how I could get that?
Find the first friction,
We got it?
and then find the perpendicular force.
The parallel, yeah. Yeah, exactly. So since it's constant velocity, the forces up and down the plane must be the same. So force applied is equal to force of friction plus force of gravity parallel. You're told the incline. So we know this is 40 degrees. So this is simply force of friction, which we have, plus Fg, and if I want the parallel, it's sine 40. Try and squeeze this in. Have the mass. We have the acceleration due to gravity. We've got sine 40. We've got the friction force, so you can figure out force applied. This gives you some number. You just plug that in. And then take the number times it by the velocity. Again, I assume you know the algebra at this point. That's not the important part. The hard part is setting up the question. So is there any questions with how I set this up? Yeah.
Remember, I don't have a question about the algebra. Actually, I have a question about the concept of power in this question.
Okay.
Like, does students exert power? And how is great power over time? And how is over time?
Mm-hmm.
We don't have the time here.
So that's a good question. So you're saying this needs to be the rate of work, but we're not dealing with time. So if I look at this equation, where does time come into play? Yeah, so it comes in with the velocity. So if I'm exerting less power, I'm going to have a smaller velocity. So there's where the time takes place. It's going to take me more time to get up the hill or up the ramp if I have a smaller velocity. Yeah. So that's where it comes in. Nope. You got the final answer? What do you got? You can try it out. It might be that. I'm going to trust that Danny got it right. Any other questions with this one? Okay. So next we move on to efficiency, which again should be familiar from last year. So whenever we're talking about machines, so remember machines can be many different things. This ramp is a machine in a physics standpoint, not in that it has some sort of moving parts to it. But anytime we do work with a machine, we always lose energy. There's going to be no situation where you don't. So when you're driving a car, you're converting the potential energy in the gas into kinetic energy of the car. Or if you are pushing down on one side of a seesaw, you're putting an input energy and the output is the other side goes up. And it's always going to be smaller. So for some examples, electric heater, this is about 95% efficient. Meaning 95% of the input comes as your output, the heat that you get out of it. A car, approximately 30%. Yeah, of course. But your average kind of car, you'd get 30%. Light bulb, about 3%. Light bulbs, Well, this might be the old school light bulbs. I don't know if that's the LEDs.
3% of the power of the light bulb turns light?
Yep. Yep. Yeah, they get really hot. It depends on what, yeah, it depends on what you're trying to get out of it, right? The electric heater, we want the heat. The light bulb, we want the light. So it all depends on what you're considering as your output energy. For which? So 3% of the energy going into the light bulb comes out as light. Because the light bulb, our output is light. A car, 30% of the chemical potential energy in the gas gets turned into kinetic energy. Because the whole goal of a car is to move. Yeah, they're not very efficient. And again, all depends on your car. They probably are trying to make them more efficient.
What's the difference between like 92 and 95?
That depends on how pure the alcohol is in the gas.
So that doesn't
Not really. It just depends on how much waste you produce with it.
the percentage of electric cars
Much higher, yeah, I think. So there's two ways we can write out efficiency. One is using work. So we do work output over the work input, and then you times it by 100%. You write it as 100 to get the percent. Or you can deal with not work, but you can deal with power. So power out over power in, again, times 100 to get it as a percent. Yes, you don't actually type in the percent on your calculator. So these are the two equations you can use. Depending on what you're given in the question, you can pick which one of those you want to utilize. Yep. Mm-hmm. All right, is anyone still writing this out? So, in calculating this, we need to remember which one is the input and which is the output. So the input is what you are doing to put into your system. So it's the amount of energy that your engine has, or the amount of energy that the potential energy starts out as. So this is either total energy, slash power, depending on which one you're dealing with, used in the process, so that you're putting into it.
Brandon, compared to calculus, the things we learn in physics are much more applicable in real life.
Yes, this is more applicable than calculus. However, Physics 12 is really simple in terms of physics.
I don't mean that
As in,
physics itself is applicable in real life. When we learn calculus or pre-calculus, I feel like most of the things we learn, I'm not ever going to use them again after I graduate. But this, I might use them.
Yeah. So, like I said, the stuff you learn in Physics 12 is very simplified. So the math that you do here is very simplified. If you want to do anything in the future that involves physics, where you need it to be more realistic, then we need to involve calculus. So you need to learn calculus first before you can take that and use it in your physics knowledge. So think about cases like tension. So when we talked about a tension question, we always assumed the string has no mass. But string has mass. So you'd need, if you wanted to calculate that, think about how, okay, normally we just had two masses, one on top of the table, one on the bottom. But now what happens if the string has mass? Part of the string's over the edge, part of the string's up by the table. So as it moves, the force of gravity that's pulling down increases as more string goes around the pulley. So how do you calculate that? Calculus. Yeah. So how does the change in mass change over time? What's the limit as as the mass changes, as the change in mass goes to 0? Have you done limits yet? Yeah. So you have to take a derivative or integral. I don't remember which one it is. But you need to involve that as you're calculating it. So I need to teach you the simplified physics before you have the mathematics knowledge to be able to apply it to a more realistic scenario.
Okay. So like the numbers we get here aren't nearly as close as what we would get with the actual.
Yeah, think about all your labs, right? We always say, ignore this, ignore this, ignore this. You can't ignore that in real life. So if you want to do something in engineering, you can't ignore air resistance, because there is air resistance. Or you can't ignore friction or say it's negligible. It doesn't work, right? So we are very simplifying this because you don't have the math knowledge yet to be able to apply that. So that's why this seems more applicable, is because first you need the math knowledge to be able to apply it to something that's more realistic.
So that when are our life
No, you just study. You just said it right now.
limits? Like the limits of calculus we took.
So the limits you take in calculus are the, I don't know if this is going to burst your bubble. So everything you learn in calculus this year is all just the foundations of what calculus is. Once you're actually going to use it, there's a way simpler way. Rarely will you use limits, but you need to understand where that comes from to be able to use it and to apply it. Yeah, to do either derivatives or integrals, you need to know where does that come from? Where does that delta x that gets closer and closer to 0, where does that come from? Taking a look at a graph and approximating what is the limit as you approach 0 from the left and from the right. So all of that is useful for when you're actually going to apply it in a real life situation. It's not that you're going to use it, but you need to know it. No? Okay. So looking at the output, so this is what is actually accomplished. So what is my output energy or output power? This is what you actually did in the process. So I can expend a lot of power pushing down on one side of a seesaw, but I might not get this, I won't get the same output on the other side. Because there's always going to be some sort of energy lost. Again, sound, heat, vibrations. So kinetic energy gets lost to the air that excites around it. You're always going to lose some energy. You're always going to have the work that you put in is going to be bigger than the work out. And so that means your efficiency is always going to be less than or equal to 100%. I say equal to 100% because there are some cases where you will have a 100% efficient some sort of process. Like what? Even that you lose energy. Well, because you need to think about what are you trying to accomplish, right? So if we're talking about, so if you're talking about just completely destroying the amount of matter in something and turning it into energy, you're not going to completely 100% going to convert all the mass into energy. You're always going to have some sort of leftover mass. Like there is something, I don't know what. I remember hearing some sort of process that is 100% efficient, but I don't remember what it is.
1 sec. Google always helps.
Google always helps. That's a good motto. I wouldn't say always. It mostly helps. All right, I'm going to zoom in for this because I need to write small enough in here. So make sure you do this small. So we've got a roller coaster. At the time of the notes, this was the tallest roller coaster in the world. I don't know if it still is. So basically what happens is you're on your track here, so the drawing can take up the whole space. You're on the track, take a 90-degree turn, and then you come back down. So this is what's happening here. So here's your cart. You got your people. They're excited. They look like ants. There's people in there. So we want to figure out a few things with this. What are we told? We know this height is 120. We know the mass of the car here is 2,800 kilograms. What else? We'll start with that. So this is our scenario.
90-degree versus turn.
Yep.
Is that all?
Not instantaneously. Not like this and then like this. But they're going from this, turning to go 90 degrees. So let's first calculate what is the minimum amount of work done on the car to reach the peak. So the work done is, what's the work done to go from here to here? So we're not really caring about the initial part, from here to here. So work, change in energy, which comes from mgh, yeah. So this is change in energy. Here, I'm going to write out the steps so you can see this. So change in energy, and we're talking about potential here, which means mg delta h. We have these values. Okay, this is the easy part. I have mass. I have acceleration due to gravity. My change in height's 120. We get 3.29 times 10 to the power of 6 joules. So a fair amount of energy. So this is just what is the amount of work done to reach the peak. So in reality, this is what's happened to the roller coaster. So we're accelerated from 0 to 193 kilometers per hour in 3.8 seconds. We want what is the actual power input in this case. So what did we calculate here? Input or output? Output. This is what we actually got out of the system, right? This is the result. We reached some height due to some initial power. And that's what we're going to figure out here. What's the initial power? Well, we have the output already. But let's figure out what this is. So I'm going to just write down here so we remember. This is the work output. Just so we know what that is. So let's look at the power input. Power, work over time. We don't know work. So we're dealing with change in energy over time. And what kind of energy are we dealing with? Kinetic. I have a change in velocity. So this is the part where I'm accelerating here. This is where the acceleration happens. So I first need to figure out what's the change in kinetic energy. So this will be a half mvf squared minus a half mvi squared. Conveniently, that's just going to cancel out. So get rid of that. You start from rest. So your initial velocity is 0. We have mass. Yes, yeah, that's from the very beginning. We have the final velocity? We have time.
You have to change kilometers per hour, meters per second.
Yeah. So first we need to take this. Meters per second should always be smaller. So 50, I think that's a 9.61. Yep, meters per second. So we have everything. We can plug that in. A half times the mass, that was 2,800, right? Yep. Over time, 3.8. What is this? 1.06 times 10 to the 6. And we're dealing with power, so this is watts. So this is power input.
We have our output.
We have the work out, we have the power in.
When we convert from work to power,
Yep. Power's work over time. So we want to figure out now efficiency. So we need to figure out what is the efficiency for this. So in looking at this, I've got work out, I've got power in. So I need to convert one of these into, either convert this into power or this into work.
can we do it from work to power?
Well, the way that I can convert that is I need to be able to have a time.
We have the time in a second.
We have time with this, so that's the only one we can do. This is not the time. Oops. This is the time it takes to accelerate. So that is the time specific to the power in. That is not the time it takes to reach the top. Can you see the difference? Power to, or the time to reach the top would have to be here. Power to accelerate is here. So I cannot just say, oh, time. I can either times this by time, or sorry, divide this by time, or times this by time in order to convert to the other. Because yeah, so this is the time it takes to accelerate. So I have to convert power in into work in using the equation. So work in.
You just said we don't have time. We have time.
Yes. This is the 3.8 is the time it takes to apply this power. So I can just use this one. So I have this number. 3.8. Yep. Uh, 4.02 times 10 to the 6. Yep. Whoops, I don't want to box that. That's not our final answer. So now that I've got the work input, we can figure out efficiency. Because efficiency, normally efficiency is EFF, so you don't confuse with energy. Is it work in over work out, or is it work out over work in? Out or in. If you ever end up with an efficiency over 100, something's wrong. This is one of those mistakes. You might have just mixed up out and in.
When I searched it up, the only machines that have 100% energy efficiency are machines that move energy and not convert it.
Okay, that makes sense. 3.29. Thank you. And then times by 100, we'll get our percent. So this gives us 82%. So our roller coaster is 82% efficient at converting the kinetic energy we had initially into potential energy final. So you can see with this how I could ask, what is the efficiency of a conservation of energy problem? How efficient is your input converted into the output? Instead of saying, what is your loss in heat, what's your efficiency? So then you would just do, what's your output? That's the final. Your input's the initial. Yeah?
Isn't energy how we create the source, right?
Correct.
So where's their space?
So let's think about a roller coaster. If the roller coaster is going from here to here, how do you think energy can be not destroyed but lost from the cart? Sound? What else? Heat, vibrations, any of these things you can lose. So there's going to be friction between the tires and the track. You lose due to heat. So we're talking about the energy of the car. So we're looking at the energy it has initially compared to the energy it has final. Looking at just the car. So in the closed system, we are also looking at the track. We're looking at the air that's around the cart. We're looking at all of that. When we talk about, here's our output, that's the energy it has out. Here's the energy it has initially. The loss is just due to the cart itself loses energy.
So if it loses energy, this thing is working faster, right?
Mm-hmm.
And things working faster, their energy converts into the vice.
No, so the car does not gain energy from its surroundings. It just loses energy to that. So think about heat. So you lose energy due to heat. So if I drag something across the floor, I'm going to lose the object itself is losing energy due to heat. Yeah, like an eraser.
Heat is an energy, right?
Heat's a type of energy. Yeah. Or the sound. So if you move your hand and you hear the sound, that is energy that's transferred from the object to the air. Yeah.
So you're saying that the surroundings cannot add power or add energy, right?
Usually they don't. So it's rare to see like, okay, if I take a heater and I heat up this cup, it's not going to give it potential. It's not going to give it any change in energy. So it's hard for me to transfer the heat into some sort of energy with the object. Now sometimes it does. I mean, depending on how much heat you do, because as you heat up an object, the particles move faster. So for instance, take a pot of water. You're using the heat from the flame and you're transferring the heat into the water. And what does that do? It makes the water particles start to move, eventually it bubbles, and eventually it turns into steam when it has so much energy. Mm-hmm.
So the car itself loses energy, right?
Yeah.
The energy or the things that are converting energy, so for example, the heat itself is energy, right? When it's applied into something, the heat itself is getting more energy.
The heat itself cannot gain energy, only other items can gain energy. So energy is energy can be transferred between different particles. So the movement of the car and the friction causes the energy from the particles of the car to be transferred either to the track, which makes the track particles move a little bit more, causing more heat, or it transfers to the air around it, so the particles around it start moving faster due to the heat that's transferred to it. So it's all about like the transfer of energy to different particles.
You have a pot of water in a cold room.
Mm-hmm.
You boil all in water.
Yeah.
Why doesn't it drain out in the room?
Because there has to be a certain amount of... It doesn't rain because that when you boil it, the steam goes into the air around it, and eventually what happens is it condensates on the outside of the walls. So it doesn't rain because it doesn't stay in the air, it condensates on the walls around it.
So could you make like a room for it to rain and boil water?
So the problem with trying to make it rain in a room is you would need, you have walls that collect the condensation in the air. Whereas when you're outside, there's no, it goes up so much into the atmosphere, it won't collect on a ceiling or won't collect on the walls, it collects into clouds. And when there's enough moisture in the air and in the clouds, then it rains. So you'd have to somehow make it so that there's not only condensation on the walls, but there's so much that it just formulates in the air and then it falls back down. So I can't imagine a way you could do that. Somehow I'm sure it's possible. That would make for a fun story. Okay, another roller coaster. So with this one's a little bit trickier. Every time I teach this question, there's always something that I make a mistake on. We'll see if this year's different. So we've got the Incredible Hulk roller coaster. You've got a car that's initially launched up a hill, traveling from 0 to 40 or 64 kilometers an hour in 2 seconds. A full car has this mass. So we want to know, oh, I remember why this is confusing, because I forget where the output and the input is. I'll remember this then. Okay, so here's what we got. We've got a roller coaster. You got the cars going up the ramp like this. Then it reaches the top, you go down, you do all the fun stuff, you do the loop-de-loops. And then you reach the end track. So we are told that this height is 34 meters. And we've got that the mass of the car here is 4,500. So we want to know what's the power output of the ride. And this is why it's confusing with the power output, because we want to know the output as in the output of reaching the top. So not necessarily of the ride, but we want to know what's the output of the initial hill. I always got confused because it said the output of the ride. I thought it was output here, but that's not what it's talking about. So in order to do this, but then it's just MVH change. See, I need to think about this. Just give me a sec. So I've got a change in kinetic energy. I've got a change in potential energy. We can calculate that. The total change is the complete output. Yes. Yep. Nope. This is right. So in this case, we've got two types of energy that are changing, right? Because I'm starting from 0 going to 64 kilometers an hour. So down here I have 0, and up at the top hill I don't have 0 kinetic. I've got some sort of kinetic energy. So I'm changing in kinetic energy. I'm increasing speed as I reach the top. And I'm changing potential energy. So I also have a change in height. So in order to do this, I need to first figure out what's the change in both kinetic and potential. I got it. So power is change in energy over time, because we're dealing with work. But in this case, it's change in kinetic energy plus change in potential. So rather than do this in one big equation, let's do it separately. So let's figure out what is my change in kinetic energy first. So this is kinetic final minus kinetic initial. Yeah, kinetic initial is 0. So we got the mass. We've got the velocity. 2 people are paying attention. What's wrong? This is a velocity. Ah. It's like the noise in the rest of the classroom starts to increase, so I throw a little trick on the board, and the two that are paying attention notice it right away. What's wrong? You seen what's wrong? So, kilometers per hour. So, converting this into meters per second, we get 17.78. So maybe it's worth paying attention while I'm in the middle of teaching. It's not as easy as you said it was. So here we go. I've now got the proper speed, 17.78. 7.11 times 10 to the 5 joules. So there's our change in kinetic energy. We increase kinetic, and we're going to look at potential. This is the easy one. mg tilt h, mass, gravity, we got the change in height, not too bad. So 45. Yep. You should see the review package. I've got a review package for the first 2 sections, a review package for the last 2 sections. Probably somewhere between 25 and 35. There you go. 1.499 times 10 to the 6 joules. I don't want that. So now that we've got those, easy, I can plug it and figure out the power. This is power output, as it was asking for. So I got my numbers. Kinetic energy, 7.11 times 10 to the 5, plus potential, 1.499. If you're freaking out at this, you shouldn't be in physics 12. Times 10 to the something. This is on all of YouTube, yeah. You should know scientific notation. Okay. And what is the time for this? Did it give us a time? 2 seconds. Yeah, so let's do scientific notation. 1.1, let's do 05 times 10 to the 6. It's like, did you guys take pre-calc 11 with me last year? I don't remember. Some of you did? All the amounts of complaining I heard about fractions. All right, any questions with this? Nope. Okay. So the actual power consumption, so the amount of power that was put into the system to get the car launched up to the top, was 1.45 megawatts. So we want to determine the efficiency of the ride. So efficiency, you have the equation. We're given the power input. We just calculated power output. Times 100, I forgot.
So is this the review?
Yep, as I had said in the first lesson, I think, when I had it with you guys, only one of the sections is new, and that's the next one. Or no, sorry, it's this, then momentum, which is on Sunday, and then on Tuesday, Wednesday is going to be the collisions in 3D.
And we used to do this on Wednesday.
Mm-hmm. So what I've covered in 3 lessons, you took last year in 7. I hope so. Megawatts just means times 10 to the 6. Just wait till you get to university where they take all of Physics 11 and Physics 12 and summarize all of that in a week. Really easy.
We think chemistry and we think calculus, يعني لو
High school is a breeze compared to university. What's that? No. So now we're told if the car pulls into the station at the end at 8 meters per second, we want to know how much heat is generated. And we want to know this since the first peak.
Sebastian, how long are lectures? Course instructions are actually.
Depends on your class how long the lectures are. I had ranging from 1 hour to 3 hours. Yeah. So we're told at the end we've got 8 meters per second. What we're looking at is how much energy are we losing. So we're looking at this equation. Energy initial equals energy final. So we're looking at since the first peak. So our initial energy here is at the first peak. The final is at the very end. So we need to look at this equation. If we write it all out, EKI plus EPI equals EKF plus EPF plus EH, because we're looking at what is the heat that we gain. So initially, we have a speed, we have a potential energy. Finally, we have a speed. We don't have potential energy, so there's one thing we can cancel out at least, which makes our lives a little bit easier. Because you're at the ground level. So what we can do with this is we can actually, what's the easiest way to do this? Yeah. See, we've calculated for lots of these already. We already calculated what the change in, but that was at the very beginning. Okay, so let's just do this. So we've got a half mvi squared plus mghi equals a half mvf squared plus eh. You have all this. You have all the mass, you have the velocities, you have the height, you're good. Plug it in. EH is 2.07 times 10 to the 6.
There's people that are coming to school and saying they don't want to come to school and they say that they can see that philosophy, right?
Sure.
Yeah, for all of that.
Sure. Well, they're not taking any tests, so how are they going to get the marks for it?
They ask all people, they do need that they go to school, that the parents will not be
Okay.
They don't assign it all the time.
There's arrangements for them to come to school. They cannot just skip the rest of all the classes. It's not possible. So let's figure out this last part. Did you have a question about this? Yeah.
So the initial velocity is like the zero and it's like kilometers per hour?
So the initial velocity, because it's saying from the first peak. So we switched the first two parts. We're just looking at this. So this was initial, this was final. We've now switched to this being initial, this being final.
Mean that kinetic final is also
No, because you're told it has 8 meters per second here. So we start off with 17, that's our initial velocity. We finish with 8. Let's look at the last part here. If at the very end, the car is brought to rest over a distance of 2 meters. So notice in this question, we're switching between initials and finals. Just like I was talking to Lila, we started initially with here's initial, here's final for the first 2 questions. Then we looked at here's initial, here's final for the third one. And now we're looking at here's initial, it comes to a rest. That's your final. So there's 3 different portions, and yes, you will get questions that look like that. So in order to do this, let's see, we're going to use the work energy theorem. And this is just the special equation that says work is change in kinetic energy, which is equal to F net times D. It's just essentially the work equation, but with specifics. So kinetic energy and F net, because we're looking at the whole car. We can figure out change in K. We know the initial speed. So we've got EKF minus EKI equals F net times D. I'm looking for force. So that's going to be what my F net is. And we're told the distance. So we're good with this. Its final kinetic energy is 0 because it comes to a rest. Brought to a rest. So then we can solve it. We've got negative half mvi squared, which the vi is just 8, times F net, which is what we're looking for, times 2. Sorry, I'm going to leave it as variables for now, D. So therefore, F net is equal to a half times the mass, which was 4,500, times the speed, which is 8 squared, over, oh, I forgot the negative sign, over 2. So F net is negative 72,000. What does the negative tell you in this question? Opposite direction, deceleration, yeah, good. So opposite direction.